Okay, part 2 of chapter 11. We're going to hit on sections 4 and 5, which is pretty straightforward on RMS value, the effective value, the RMS value, and we'll get to what RMS actually means. But it's this will move right along. So the effective value, I like this statement in the book, so I just copy it and use it, of a periodic current. Now remember, this is the word, pay attention to the word here, periodic. And this is written in terms of current, but voltage is the same. The effective value, it's periodic. This does not say sinusoidal. It is not sinusoidal. It's periodic. So it can be an odd shape, and there's a lot of wonderful problems, examples, and practice stuff in the text that the authors have put together deliberately using non-periodic waveforms. So using non-sine waves. The important element is that they're periodic, okay? So it's the DC current delivered by the same average power to a resistor as a periodic current. Okay, so what this is trying to do is this means it's trying to say what's the value, I'll use the current, what's the value of the waveform, what's the value of the current that's equal to the current if it was DC, right? So in simple terms, it's going to try to make the equivalent to a simple battery. If I replace the DC source by a battery, if you didn't have the AC signal to plug into the wall in your house and you wanted to replace it with a battery, what would the size of the battery be that you need? What are the power characteristics, voltage and current characteristics? Those are the effective values, and effective, you're going to find out, means RMS. It's just a terminology. But the key thing is, how do we relate a DC value to a periodic value in terms of its energy transfer and its overall usefulness there? Okay? So here is that simple circuit, our simple circuit, with an AC source, time-varying source. So this is an AC circuit, voltage and current across a resistor, coming to a resistor. Okay? And we want to compare that to a DC source across that same resistor producing an effective current. Okay? Now this is time varying. Right? These over here are going to be time varying of some sort. This is going to be the DC equivalent. Okay? That's what's going on here. And it's important to keep that in mind. Okay? Okay, so in the AC circuit, we've been through this already, so I'll move through it. The average value is the time average of the power. So we're averaging the power, right? And we've done this before. So this is a time variable element. R is constant. But we've done this before. So it's pull out the R over T times the integral of the current squared dt. On the DC side, we simply have the effective voltage, and we haven't calculated this yet, the effective current squared times R. Okay, that's exactly what we're headed for. We want to find out what is this that creates the same power transfer as this. So what we want to do here now, we have some simple where's my pen? We have two versions of power, one on the AC side and one on the DC side, right? AC and DC. All right, so if we equate these two, what do we get? Right, if we equate them and solve for the current, okay, I'm going to just well, let's just take it a few steps then. I squared effective times R equal to R over T integral 0 to T I squared. Now we can't just dismiss this because this is really I as a function of T, right? You can't be casual about that and say, oh, well, that's a constant. It's not. Okay. Here goes the R. We can get rid of that. I got a square here. So the effective value is equal to the square root, I'll leave myself plenty of room to write 1 over T integral of 0 to T of I squared, and I'll include it, I squared of T dt. Okay? So this is the root of the mean square. So here's the root, the square root of the average value of the squared term. Okay? So what am I doing here? This is saying I squared the term right there. I squared it. Then I took the average value, then I took the root of it. So that's why we get root mean square. And what's really happening is it's in mathematical terms, you take them the opposite way. You square something, you take the average, the mean of it, and then you take the root of that result. in smooth equations, like sine waves, this all becomes, routine integrals. When the functions are more interesting, square waves or triangles or combinations of those, as long as they're periodic, this integral may turn into a summation sign. It doesn't matter. What are you doing here? You're finding the area under the square of a function. Okay? And that's what's going on with root mean squares. So you can do root mean squares, RMS values of all kinds of things. In fact, we generalize the term like this. We just say that if I have some function x, if I take the square of it, and then take the mean of it, and then take the square root of that, I have got what I call the RMS value. Okay? So I take the square, then I take the mean, so that's this, then I take the mean, and then I take the root. The root mean square. It's always that process, and it really doesn't matter what the signal is or what the entity is inside. It's a general mathematical term, okay? If I do it for our current that we have, here's that equation, right? Here's our, and I've taken away the offset, right, the phase, because we're only looking at the isolated term. So I am cosine omega t, here I square it, I need to square the magnitude and I square the cosine, integrate that, so take the area under the square, average it, and then take the root of that. Okay? Now when I take the square of a cosine, right, we might want to take a little look at that, since, Let me go backwards. I don't want to rush it here. Here we are with this. Let's say, right, just for the picture's sake, here's our cosine wave. When it is squared, what happens? You've got this value is squared, so it's going to be maximum. This value is squared, so whoops, so here it comes down. These are all squared, so now they come up positive. So now you got this thing bigger, but it's all positive. Okay? So now let's see what happens. Now if we do that, we've got, I'm just following through on the math. This is straight out of the text. So you have this. And where did this come from? Did they just whip that out of the text? No, that's back to our, cosine AB. These are just trig lookups. The cosine squared of omega t can be written as, right, this thing here can be written as all of this, right? That's just a trig lookup, right? A trig lookup. So, like I said, keep that book or keep a reference or whatever you're going to do, however you want to do it. Keep it close to you, because you'll be looking in there now and then. This whole thing amounts to, I don't mean just that one point, this amounts to Im over the square root of 2. Now, why is that? How does this come down to something so simple? Well, the square root of Im squared, that part's easy, right? Im. If I take the integral of this over one period, there's maybe an interim step in here that I could say, this whole thing, what the average value over a period is going to be simply 1, right? That's part of what's going on here. If I take the average of this and divide it by t, this whole thing divided by t, the average value of this, if I integrate it, is t, right? And you know that because if you take the integral, you're going to get it evaluated at 0 and t, and you're going to have a, you can look up the integral of that. You're going to have a t plus something, and that's going to evaluate to t over that integral. So then t over t is going to equal 1, right? So you're going to be left with this 1/2 as a constant. So the square root of 1/2, that's where this comes from, right? So this is always going to happen, folks. And if you probably have heard, you remember, you'll see this is equal to 0.707 Im, right? Because the square root of 2 is 1.414. And believe me, you're going to see these numbers over and over again around sinusoidal waveforms. So in house power and house current and everything, these numbers are over and over and over again. Okay? You can go through the same thing for voltage. You'll end up with a similar thing. So when we say the house voltage, right, is in a house, you got 120 volts AC, we're really talking about this. 120 volts AC at the wall is really this. It's VRMS. It is not the maximum value, because this is what delivers the power, okay? So now if I look at the power of the whole thing, I've got, where did this like magically occur here, this 1/2? Well, that's because this was Vm over the square root of 2 and Im over the square root of 2, okay? I'll copy that in. So there it is, Vm over the square root of 2 times Im over the square root of 2, right? And when you multiply that out, you've got what? VM VRMS over IRMS, right? So don't think here, don't think as I did for a moment that, oh, well, let's go backwards. Come on now. That like I did, that somehow I was suddenly going to what happened to those square root of 2? Square root of 2 times square root of 2 is 2, but that's not what's going on here. This is VM, and this is VRMS. So the point of this is it's made a nice, tidy formula. And the next one is just the power is I squared R or V squared over R. Now what's the beauty of this? If you use RMS, funny things like square root of 2 and that go away, and this looks a whole lot like the results from Ohm's law and the simple power equations, right? So let's go on now and finish up. We can do this quickly with section 5, apparent power and power factor. This is where we're going to be back with phasors and phase diagrams. So the book puts them under the same title. They're actually kind of two separate things, but they are very related. The apparent power, that's simply the product of RMS values, right? It's what we had right back there. If I have, so it's VRMS times IRMS, just like we ended the last section with. All right, if I take the sinusoidal waveforms, right, and I go for the real power, the instantaneous power, this is what I have, right? We did this already. This is what I have for instantaneous power. What I'm saying now is we get apparent power by saying it's the product of the RMS voltage and the RMS current. Okay, so here we have that. There's RMS voltage coupled with that, and here's our RMS current coupled with its phase angle. So these two things, if I have a diagram here, now we're at this point, they are not assumed to be in phase. The only time they're going to be in phase is if I have a purely resistive load, right? So I could have voltage here, right? So this is at some angle theta V, and I could have current up here, right? And this is at some angle theta I, right? I could have that. What we're saying is the product of the two RMS voltages is the apparent power. We're just giving a name for the product of the RMS values. At this point, we do not know how much of this is real power and how much is reactive power. All right? There's no rule that says one of these has to be sitting down here on the real axis. They can be wherever they're going to be. Okay? So, to emphasize that much is the apparent power. So that's just a term, a definition of a term, apparent power. Okay, so we're done with apparent power. Easy, huh? Now let's go to power factor. And this is the part that gets kind of buggy because the power factor tells us how good is our power, how much of it is buying us action. Basically, how much is real and how much is reactive. Okay, so the power factor definition here, cosine of the phase difference between voltage and current. It's also the angle of the load impedance, right? So that's going to be the same angle. The load impedance has a real and an imaginary part, right? It's a complex number. And as such, that enforces the difference between the voltage and current. Now they could be rotated relative to, a 0 degrees and 90 degrees and all that. But that angle between them is what's going to determine the power delivered to the load. Okay, so the voltage, the power is then the RMS voltage times the cosine of that difference in angle. We saw this already, right? We saw this already. What we want to know is, what's the power factor? So it's a definition. If I take the cosine of the difference in those two angles, that's the power factor. Now what does it represent? Look here. I've got this formula stretched out. So what is it? It says that the cosine of those angles, if I divide this, whoops, come on here. I do hate when it does that. If I divide this by S, right, that's the same as dividing this by S, but I don't care about that one. I want to divide this by S. Boom. I've got cosine of the two angles right there is equal to P over S, right there. That's my definition of the power factor. Okay, so kind of what does it represent? This is the effective power product, right, which is something at that angle, times the apparent power. So you might ask yourself, what's the range of this? Can it be 0? Can it be 1? Can it be 10? Can it be 5? What can it be? Well, right away, if it's defined as the cosine of anything, the power factor is going to be a number that's greater than or equal to 0 and less than or equal to 1, because that's how the cosine runs. Okay? And you can kind of guess, you'll figure this out as you see things happen, that what you'd love to do is get the power factor to be 1. Right? How does it get to be less than 1? Well, if the power delivered, look, this is the raw power available. This is the power that actually gets there, right? So this is available, and this is delivered. Okay? So you're never going to deliver more than you have to give, but what you want to do is deliver as much as you have to give. And that's what's going on with power factor. That's why we even have it. Okay, so let's look at this in terms of the Z, the load impedance. It's also the cosine of the angle of the load impedance. So here we are now in vector terms, talking about impedance. So these are vectors. Let's put them as vectors. The maximum at an angle of theta v and the maximum at an angle of theta I. So here is the definition of the impedance, right? It's the ratio of the magnitude. That's like voltage divided by current. This is like Ohm's law, right? Except we invoke the angle here, right? So in picture terms, like pictures, this is like, here's Z, and here's the angle theta. So somehow that's the real part, and that's the imaginary part. Okay, so if I broke this out and want to define this, Z would be equal to V over I, the maximums, V over I times what? The real part is going to be the cosine of theta v minus theta I, and plus j Vm over Im sine theta v minus theta I. Okay, in other words, it's just the projections of that angle. Okay, so where does this go then? This just I don't know why I repeated this. Oh, so this is now just expressing it in terms of RMS values. Okay, you can do that, right? Because all you're concerned about is the ratio of maxima and the ratio of RMS. It turns out it's okay for them to be the same. Okay, so that's power factor. It's how well were you at delivering to the load. Okay, so I'm going to quit here for sections 4 and 5. There will be one more video in the chapter on complex power, which really just takes the further extension of this angle, the angle that's involved. Okay, see you for that one.